Now, I'm going to derive what our plug and chug method is from first principles, from differential equations. I want you to see this, but I don't want you to get overly hung up with exactly how it's derived. I'm not going to ask you to derive it on an exam. I'm only going to be asking you to use the plug and chug equation, but I still want you to see its derivation, so it's not just something totally out of the blue.
Sir?
Yeah.
Jake clicked. He just disconnected his laptop died. He's joining back now.
Okay. So we're going to start with a subset of problems. We're going to start with just looking at an RC circuit, and I'm going to look at its natural response. And for those of you in differential equations, you know that the natural response is what you get when there's no external forcing function applied. So what that corresponds to in a circuit is if you've got a capacitor and it's got some sort of initial charge on it. Let's say I'll call it capital V of naught. And here's our capacitor. We're going to connect it to a resistor. And you can see that it's going to have, there's only one pathway for current to flow around. We'll call that I. It's both I sub C and it's I sub R, so there's not much reason. So this is our capacitor over here. No reason to call it I sub C or I sub R because it's the same I. And we've also got some sort of voltage over here. So we're going to call it V sub R. Now, let me be kind of clear about what these different variables are. Our I is the current that's flowing around our circuit. And let me actually change the way I write this. When I write something in a lowercase, it means it's changing. And if I write something in an uppercase, it means it's static. And this V sub naught is going to be equal to the voltage on the capacitor at time equals 0. So this is the circuit for time greater than 0. I plugged in a charged capacitor into it. It's going to discharge through the resistor, and that capacitor has some initial charge. Can you see why it doesn't make sense, why it's not an interesting circuit if it does not have this initial charge on it? If I plugged in a discharge capacitor and put a resistor across it, there's nothing that's going to want to make current flow. So it's going to be 0 everywhere. But as I've drawn it, the hydrodynamic analogy would look like this. So again, I'm only drawing these things for time greater than 0. For time less than 0, it had to be different because it had to be different if this charge is on the capacitor at time equals 0. So I've created this circuit at time equals 0, and it's got this initial charge on it. And I want to find the relationship between the current and the voltage and everything else in it. So now I'm going to use just your own intuition. And I want to take a look at that, at the current versus time. So Stone, tell me for this circuit, or for this thing equivalently, what is our initial current at time equals 0? We've got an initial charge on this capacitor that's pushing with a force of V sub naught. We've got this resistance over here whose value is R. What is our initial current that flows at time equals 0?
Some value above 0, and then it's going to decrease as the voltage, I guess, drops and the pressure drops from the
Sure, that's absolutely true. It'll look like this.
capacitor.
But I want a number for this. If I've got or an equation, the initial voltage pressure across the area is capital V sub naught, and the resistance is R. So what's the initial current going to be?
For your voltage, and then you have a resistance.
Right, and so that's set by Ohm's law. So what would that be? You know your voltage. That's the voltage across the resistor. You know the resistance. So what would that initial current be?
Just P over R, unless we're
V
dealing
naught over
with
R. That's all.
Yeah.
V naught over R. And of course, then it goes down by some speed, and we're not exactly sure how it goes down, but we know it's going to look like that. And if similarly, we wanted to graph a picture of the voltage in this circuit. Let's say I want to talk about the voltage across the capacitor. So that's the voltage on the left. Got to be the same as the voltage on the right. Pavel, what's that voltage going to look like? I've already said that that voltage starts off at V sub naught. And how's it going to work with time?
Isn't it going to do the same thing as current?
Exactly. It's going to start off with this diaphragm fully charged with a lot of pressure against it. And then that water is going to move around in this direction. And over time, it'll gradually discharge that diaphragm, and so it will go down. So even though it's got two different units here, it's going to look grossly similar. So that is the intuition that I want you to keep in the back of your head as we derive what's going on with this.